Assalamualaikum, my name is Nur Shasha binti Abdul Aziz.
My name is Nur Arina binti Muhammad.
My name is Anas Ashrawi bin Azizi.
My name is Muhammad Nazmi bin Sobri.
My name is Nur Aina Nabilah binti Kamarudin.
Centella asiatica has been used as a traditional herbal medicine in Malaysia and other parts of Asia for hundreds of years. This tropical plant has been reported to have been used for various medicinal purposes such as wound healing, treatment of asthma, ulcers, lupus, vein diseases, memory improvement, as an antidepressant, antibacterial, antifungal, and anti-cancer agent. Based on the several studies, the biologically active ingredients are believed to be its triterpenes, namely acetic acid, medicacic acid, aceticoside, and medicacoside. Triterpenes being the major components of Centella, they have been regarded as its biomarker components. Therefore, the leaf of Centella asiatica were analyzed for their triterpene composition due to its bioactive compounds. Most studies for quantitative analysis of triterpenes in Centella asiatica are commonly carried out by high-performance liquid chromatography and gas chromatography.
For my part, I would like to explain about the procedure for extraction of triterpene components from Centella asiatica by using HPLC methods. It consisted of several steps. Firstly, Centella asiatica, which obtained from the local market, was washed with running tap water and rinsed by distilled water to remove any dirt and contaminant on the plant material. Then, clean plant material was stored in the 50 degrees Celsius control oven and left to dry for 3 days. The dried plant material was ground using a conventional rotor. The dried and powdered material was then undergo milling processes in order to produce Centella asiatica nanopowders. Herbal nanopowders are the herbal powders ranging from 10 to 1000 nanometer in size. It has unique properties such as larger surface area, thus increase the extraction ratio of bioactive components from 17 to 50% increases compared to the normal powders. Besides, it will save time consumed for extraction, and it just only requires small portion of powder as the supply of raw material is limited nowadays. So the resulting milling product is then further used for extraction. During extraction, the mixture of 0.6 grams Centella asiatica nanopowder, which was weighed and mixed with 50 ml water, was then sonicated for 20, 40 and 60 minutes by using ultrasonic processor. Then, mixture was centrifuged to separate the particles and filtered by gravitational filtration. Filtrate was collected and water was removed by freeze dryer, and weeks of crude extracts were recorded. The extracts were dissolved in methanol and filtered through filter paper before being subjected to HPLC analysis. During HPLC analysis, this is where the individual's content in the extract was analyzed. Solvent A, methanol, and solvent B, acetonitrile, were selected as the mobile phases, which are the pressurized liquid. The column temperature was maintained at 25 degrees Celsius. In column chromatography, a solvent drips through a column filled with an adsorbent under gravity. HPLC is a highly improved form of a column chromatography. A pump forces a solvent through a column under high pressures of up to 400 atmospheres. The column packing material or adsorbent or stationary phase is typically a granular material made of solid particles such as silica or polymers. The pressure makes the technique much faster compared to column chromatography. This allows using much smaller particles for the column packing materials. The small particles have a much greater surface area for interactions between the stationary phase and the molecules flowing past it. This results in a much better separation of the components of the mixture. The components of the mixture are separated from each other due to their different degrees of interaction with the absorbent particles. This causes different elution rates for the different components and leads to the separation of the components as they flow out the column.
I would like to explain about analysis HPLC. Firstly, extraction of active chemical compound from natural sources is the most important research area in pharmaceutical and chemical industry. Bioactive compound extraction aims to get a better extraction yield and less time consuming without altering the structure of compound extracted. However, the extraction efficiency of this method is greatly dependent on the particle size of plant material. The concentration of acetic acid, medicacic acid, acetylglycoside and metacoside in Centella asiatica crude extract was quantitatively determined with HPLC analysis. Centella was found to contain significant amount of metacoside. Metacoside is the highest component in Centella at concentration of 3.10 plus minus to 4.58 mg per ml, more than acetylglycoside, which is 1.97 plus minus 2.68 mg per ml, and acetic acid 0.55 plus minus 2.29 mg per ml. There are the difference between the acetic and medicacic acid in the sugar glucose ramos, whereby for the aglycone, the sugar molecule is replaced by an OH group. Centella extract show stimulatory effect on collagen synthesis. Centella extract at higher concentration than 50 mg per ml success to decrease the cell visibility. Stimulation of collagen synthesis is important criteria for plant to extract to be potential ingredient in the skincare. In skincare product, for restoring skin firmness, elasticity and improving skin appearance. Last but not least, the most important point is the triterpene that have been found in extraction of Centella asiatica show to offer a number of beneficial activities to the skin, including wound healing.
For my part, I would like to present about method that I will research to extract of triterpene compound from Centella asiatica as treatment of wounds by using gas chromatography method. Based on my research, I have found there are 3 steps to extract the triterpene of Centella asiatica. Okay, firstly for conventional extraction step, the powder of Centella asiatica 2 kg was macerated with 70% ethanol at room temperature for 48 hours. Then the extract was filtered through filter paper and the filtrate was evaporated at 50 degrees Celsius to remove the solvent using a rotary evaporator until it was completely dry. Next, for the step 2 is sample extraction for Centella asiatica. First, the ground sample was mixed with the 10 ml of acetonitrile in a 125 ml conical flask. Then, shaking it for a while and left it at room temperature for 15 minutes. Then, the liquid that was extracted centrifuged for 10 minutes at 2000 rpm. After that, move it to another conical flask after passing through a filter funnel containing a glass wool and anhydrous sodium sulfate. The leftover sample extract was applied again. The liquid extract was collected in the same flask with the first liquid extracted. This method has been replicated for another time. After that, with using pasteur pipette, transfer to a 10 ml of glass test tube the liquid that was collected. After finish it, the flask was rinsed with 2 ml of N-hexane. There was a concentrate extract blown down to 1 ml with nitrogen gas. And for the last step is clean up process. Firstly, the objective of this extraction is to clean the procedure by using a column that containing 5% active silica gel and anhydrous sodium sulfate, which column has been wet using 10 ml of N-hexane. Then 1 ml of the concentration of the extracted substance was pipetted into a column and it is illuminated with 10 ml of ethyl acetate hexane, which is 1:1 ratio. In this step also, I have used triterpene, a formula to find the concentration of triterpene. This formula is M1V1 equal to M2V2. With using this formula, I can identify of triterpene residues in leaf extracts.
Based on the result, the response factor was created by the calibration curve slope with a GCMS resolution of 1000. However, triterpene were detected in 6 samples with a different handling methods, where in 3 samples treated with salt water, A1, C1, and E1, and in 2 unwashed samples, E1 and F1, and in 1 sample treated by tap water, which is E1. The triterpene found in A1, C1, and E1 that had been treated with salt water contains the highest concentration of triterpene compared to the other handling methods. Sample A1 contains the largest triterpene concentration, which is 19.78, while the C1 contains almost half 8.53 of A1, and sample E1 contains triterpene at 0.99. The high triterpene concentration observed in samples A1, C1 attributable to the extraction time. Within a week of sample time, all samples were collected, while the other samples were extracted later than that. Due to its elevated volatilization rate, the storage time will impact the volume of triterpene. The triterpene may be degraded to a certain level that is caused by the storage temperature. The triterpene with a triterpene of E1 with a concentration of 0.44 is only found in 1 sample treated with tap water. The lowest triterpene content found in all samples in this concentration in E1. Thus, the most effective handling method for cleaning Centella asiatica before use is treatment with tap water. The unwashed samples from plot E1 and F1 have demonstrated the presence of a low triterpene concentration of 0.53 and 0.77 respectively. The concentration, however, are far below than the maximum residual limits. The growth coverage of Centella asiatica on these plots can be explained by the undetected triterpene in samples from plots B1 and D1. Compared to the unwashed samples and samples treated with tap water, the concentration of triterpene in samples treated with 200 ml of 0.01 gram per milliliter of salt water was higher. Even so, the outcome of this analysis reveals that salt water is not ideal for soaking Centella asiatica because the triterpene has not been diluted. GCMS is known as one of the most comprehensive analyzers for bioorganic compounds from plant origin. Centella asiatica has triterpene that we would like to study in details. Unfortunately, due to the complex constituents, GCMS is not suitable for volatile compound, which is triterpenoids. However, HPLC and LCMS can be used to analyze and study the triterpenoids compound. Centella asiatica is the multi-purpose traditional medicine that has been modernized better for modern medicine due to its benefit towards skin and wound healing. As triterpene is the major biologically active ingredient in Centella asiatica, triterpene can be found in highest concentration when the Centella asiatica is rinsed and soaked in distilled water or tap water for an hour before extraction. Therefore, triterpene really helps healing wound for any type of skin because it's very gentle.
In conclusion, Centella asiatica has been introduced in modern medicine as an alternative remedial solution and has been included clinical studies as a topical remedy for skin ulcers and wound healing. Triterpenes are the most active group of compounds located in Centella asiatica. The largest triterpene glycoside is aceticoside, which promote wounds healing and can boost the antioxidant levels at an early stage of wound healing. Triterpenes are usually present in many plant oil constituents. Thank you.
Thank you.
Thank you.
Thank you.
Thank you.